tell artificial intelligence what kind of world we want to live in. And this AI would show us how to get there. Imagine having that power. We could tell AI to reduce crashes, eliminate forest fires, or even design the best economic policy. This AI would show us what actions we need to take to get to that future, that utopia. So this would be great. How can AI create utopia? This is the question that we're asking. How can AI design an optimal world and help us make better decisions? To answer this question, we first need to look at how AI is being used and developed today. Today, most applications of artificial intelligence involve answering questions. Questions like, is this image of a cat or a dog? Or is this a fraudulent bank transaction? These are the types of questions that AI is learning to answer. AI learns by looking at human answers. So most of today's artificial intelligence learns from humans. And this approach is extremely useful and has a lot of applications, as we know. But it also has limitations. Number one, this AI is only going to be as good as the data that we provide to it. And number two, since this type of AI relies on our knowledge, it's hard for this AI, this type of AI, to solve problems for which we don't have the answers. If we want AI to teach us how to improve the world, it cannot rely on human knowledge. It needs to discover its own answers to questions. So what if we only provided goals to artificial intelligence, and the AI itself would figure out what actions it needs to take to achieve those goals? If we do this, AI won't be limited by our knowledge anymore. It would allow AI to solve problems that we don't have the answers to. And in fact, there is a type of algorithm that can learn to achieve goals without relying on human knowledge. It's called reinforcement learning. Reinforcement learning is a term that actually comes from psychology. It's about 100 years old, and it's all about learning from rewards, learning what actions to take in order to maximize your reward. So let's say we have our AI agent, Mario, over here, right? And Mario exists in his world, in his environment, this 2D flat screen. And Mario's goal, we give the AI a goal, so Mario's goal is to get to the end of the level, to get to the objective. And so he needs to figure out, our AI needs to figure out what actions to take in order to reach that goal. And the AI knows about the goal in the form of a reward. Let's say every time Mario moves a bit to the right, a bit towards the goal, Mario, the agent, receives some reward. And so with reinforcement learning, what's happening is that our AI is learning how to take actions that lead to getting more reward. It tries different things and learns the correct strategies. So we learn which actions get more reward, which actions get us closer to our goal. Importantly, reinforcement learning doesn't necessarily rely on human knowledge. We give the AI a goal, like get to your objective, right? And the AI learns which actions get there. It doesn't rely on human knowledge, and that's really important. Now, for the AI to learn, we might need to go through this loop hundreds of millions of times, possibly. It needs to try many, many things, because at the start, it doesn't actually know anything. At the start, it's taking just random actions and seeing what's happening. Eventually, it'll learn a strategy. That's why, for training these reinforcement learning algorithms, we need simulations. Simulations of reality. Here we see a reinforcement learning algorithm training to operate a four-legged robot, quadruped robot, inside of a physics simulation. So inside this physics simulation, it's learning to walk up and down stairs over rough terrain. And this is research that was actually done. And what the researchers did, they trained their AI model inside of a simulation. And then they took this model that was trained only in simulation and put it inside of a real robot in the real world. And even without any training in the real world, just the simulation, it was able to walk up and down stairs, to walk over rough terrain. Because this is an accurate simulation of physics, or accurate enough, right? So RL learns reinforcement learning, learns how to achieve goals inside of a simulation, and then we can transfer that knowledge to reality. Great. So what can we actually do with this technology? What is being done right now? Well, what if we wanted to design the best laws or the best economic policy? We could tell AI, artificial intelligence, our goals, and it would hopefully discover which economic policy best achieves our goals. How would this work? Well, we'd have a simulation of an economy, and then we would say what we want the market conditions, optimal market conditions to be, and it would try many different things we even couldn't try in real life. And the hope is that we actually get strategies or economic policy that's better than what we could imagine ourselves, because it can try all these millions of different possibilities inside of a simulation and formulate strategies there. And this isn't fiction. This is actually real. Recently, IBM released a paper called The AI Economist, in which this was done on a smaller scale, a simulation of a market economy, and the AI was controlling the economic policy in order to achieve certain objectives. So we could use AI to develop possibly optimal laws and economic policy. What else? Well, what about city design? What if we wanted to design an optimal city? Again, we could give our goals to a reinforcement learning AI agent, and inside of a simulation of a city, the AI could discover how to achieve these goals. Maybe you want more trees and greenery. Maybe you want to optimize the placement of solar panels in the city. Maybe you want to optimize the placement of cell phone towers. And this, again, is not a fairy tale. This work has actually been done using reinforcement learning to optimize the placement and positioning of objects in our city. And I've been working on something in this realm over the past few months as well, reducing crashes with AI and simulations. Take a look at this picture for a second. You might notice something. There's a woman right behind that car there on the right. And if a driver wasn't careful enough and they were going to turn right, they might not see the woman because she's right after that car, right next to it. So this is a possible scenario, and this is a place in a city where there could be a lot of near misses and unfortunately crashes, right? So what I've been working on is giving AI the ability to look at these places and tell us what is the problem and how can we fix it. So we have data, lots of data, about where do crashes or near misses occur in a city. We build a simulation of that road segment or area, and then this reinforcement learning agent manipulates the scene and determines what was the cause and what we should do to fix it. So the AI would tell us, hey, that car shouldn't be there. It's causing a lot of near misses in my simulation. I discovered that. You should put a sign that says, don't park here. That's something that the AI could help us make better decisions using simulations. As climate-driven disasters become more common, we'll need better ways of managing disasters and providing relief in real time. And by running this type of AI in simulations of these disasters, we can determine what are the best actions to take. And we could even do this live. So for example, in firefighting against forest fires, AI is being used to determine the optimal placement of firefighters, of helicopters, and if we have a section of, let's say, California that we know there are often forest fires, we can really have a simulation of that location ready to go at any moment. And we just plug in the parameters of the fire, and we have a fire spreading simulation, and we see the RL agent will figure out what is the optimal path we should take to suppress this danger. Should we evacuate here? Where should we send the firefighters? And it tries all this much faster than we could, and it can make mistakes that we can't afford to make. So hopefully, it learns better strategies than we could imagine. What about robotics? Robotics is a rich field of study for artificial intelligence, and specifically reinforcement learning. Number one, reinforcement learning is used to control the low-level joint actions of robots. We tell the robot the goal. Pick up that cup, walk over there, jump over this hill, do a backflip, right? And the AI will learn what joint torques to apply to the robot in order to get the robot to do that action. And again, we're not giving the answers, we're just giving the goals. The AI is figuring out how to do that by itself. But not just low-level joint control. What about clean the house or clean up the street? These are goals that we can define, and the AI needs to figure out what sequence of actions, high-level actions to take. Go to the kitchen, put the dishes in the dishwasher, all these different actions need to be done in sequence, and reinforcement learning can figure out what actions need to be done in order to achieve our goal. That's the goal of reinforcement learning, figuring out actions that get us the most reward, that get us closer to our goal. And we could go even more low-level than this, to the level of chemistry and molecular design, material design. Reinforcement learning is being used to design optimal materials. Algorithms are literally placing atoms inside of simulations and seeing how conductive the material is. So if the AI is rewarded based on the conductivity of the material, it will hopefully discover how to design the most conductive material. And it could, again, try many different things inside of simulations that we can't afford to do in real life because either we don't have the time, or we don't have the money or the means to try all those different experiments. But the simulations and the AI make it possible. So this seems like a really promising direction for how to try to achieve an optimal world. Having AI try different things and learn the best strategies inside of accurate simulations of reality. But as we come towards this point, we also need to be aware of the dangers that are associated. One of the dangers that happens to occur sometimes are sub-goals. Sub-goals are a lesser goal that is formed in part of a greater goal. And these are things that we might not have control over as programmers, as developers. Let's say we're telling an AI to improve living conditions on Earth, and we give it some metrics, right? That's the goal of the artificial intelligent agent. But what if it eliminates half of life on Earth in order to improve living conditions? That's something we definitely don't want to happen, and that's something that we don't align with. That's not one of our goals as humans. But this is a danger that we must account for, these side effects or sub-goals that the AI comes up with when it's trying to actually satisfy our requests. We need to ensure goal alignment between AI and humans so that our future is a positive one, that it's not happening all these sub-goals that we don't actually align with. We want to make sure that our goals and the machine's goals align. We can't stop progress, but we can only prepare for the future. And this is why we need to ask these questions now and investigate them. And that's why the field of AI safety research is extremely important. In AI safety research, what we're doing is asking these questions and actually investigating how to answer them. Because when we have something like goal alignment, we're asking, how do I align goals? How does that work? Well, there are a few theories. One of them is if we give values to the machine, maybe if we give the machine values, then values that can't be broken, right? These internal rules that it'll follow, then we can ensure goal alignment between humans and AI. But that has some trouble. First of all, we don't know how to encode rules into a machine that definitely 100% can't be broken. With reinforcement learning, it often finds these little paths that we didn't think of to kind of skirt our rules. So that's something we need to work on. And also, there's a political question. Which values do we encode into the machine? As cultures change around the world, values change around the world. So is one set of values better than another? How do we choose? Should we choose? These are questions that the field of AI safety research is tackling and actually trying to implement inside of these machines. By running artificial intelligence inside of accurate simulations of reality, we have the chance to discover optimal decisions and design a better world. If we remember to ask questions beforehand and prepare for this future, then we might really have a chance at creating utopia. Thank you.
Shalev, that was impressive. And I was asked by so many people if that session was streamed and put on the webpage. We will check for you, and I will let you know later. Woo, I have lots of questions in my head. I was laughing very hard at the very beginning when you said, like, it would be a problem if AI would just learn from humans, because whenever I have an issue with my laptop, I call my dad, and he always says, Susanna, first of all, the problem is in front of the computer. And then we start. So I was like, yeah, but that was a personal thing. I have so many questions in my head from my side. But of course, I would like to give you guys, first of all, the opportunity to ask questions to Shalev. Are there any questions from your side? Just raise your hand. There we are.
Thank you so much for this really interesting talk. When you said reinforcement learning does not require human knowledge, but I mean, it's a human who codes the simulation and the humans that defines the goal. So isn't this also some kind of human knowledge that's required for reinforcement learning?
That's a great question, and yes. The answer is yes. It does require that sense of human knowledge, for sure, because we need to build the simulation that the AI is going to take part in. For example, if we're creating a simulation of physics. In fact, there is AI that learns physics, but that's another story. Usually we use simulations that we build ourselves. And so what happens is essentially we do the work at the start to create a simulation, and then it relies on that human knowledge. And actually, you know what, now that I think about it, let me rephrase. Reinforcement learning doesn't necessarily rely on human knowledge, because an RL agent can learn just from a robot in the real world. It can learn to walk, let's say you have a robot that's a car trying to get somewhere. There's no simulation. Of course, we need to code the algorithm, but once we've coded the algorithm, it can learn by itself. That simulation that I mentioned, yes, that is another piece of human knowledge that makes it faster to learn, because it can try millions and millions of things faster than reality, and that we use that simulation to allow the AI to make mistakes where we don't want it to make mistakes in real life. But the key is that we're not giving the AI the answers to questions, which we do with something called supervised learning. This is most of the applications in industry that exist today. What we're doing is just providing the goals in form of reward, and then letting the AI determine what actions to take. And then it can kind of get these optimal actions that we wouldn't have thought of, and hopefully better than us, right? But great question.
But inside the simulation, how does the AI know which actions it can take?
So ties into your question as well. What we provide to the reinforcement learning agent is a set of possible actions. We give it an action set and say, here are the possible things you can do inside the simulation. Now you figure out what to do. I'm not going to tell you what to do. Here, I'll give you reward when you do something good. I'll give you negative reward when you do something bad. But you figure out what to do. And then through this action set, it figures out when to perform the best actions.
Is it like a trial and error all the time?
It is trial and error, but the key one question you may ask is, well, what's the point of this? Why don't we just try all the actions, forever? But think of a game like Go, where reinforcement learning has been applied and beat the world champion. You cannot try all the actions because, I don't know the exact number, but it's just unfathomable to try all those actions. Like, there's just the number of paths is too great. And so instead of trying all the actions and brute forcing it, what we have to do is actually form strategies. And that's what reinforcement learning does. It forms strategies, and it doesn't just try everything. But yes, at the start, it'll do some trial and error, so it can figure out what strategies to use, basically.
Awesome. There was another question over there, I think. Yeah, perfect.
Yeah, it kind of comes along with the question that was just asked. So let's take the forest fire, for example. We set the parameters, right? So California, how many trees are there? What kind of trees? Yeah. When was the last time it rained, etc.
Yeah.
Isn't it, if we miss one detail, let's say the last time it rained, the whole simulation is off by so much that the answer it actually gives us could even provide us with a worse advice than maybe humans would have? Is that realistic, or are we so good in setting the parameters that we are very sure that the AI at the end gives us a good suggestion?
Yeah, thank you for that. That's another really, really good question. So yeah, I agree with you. The parameters are very important. What we want to try to give the best parameters possible. So if I'm thinking about something like forest fire fighting, right? Firefighting a forest fire. I guess we're trying to think of what what are the parameters that are the most robust we can provide to the AI? So maybe something like last time it rained, that's pretty accurate, but maybe we can get live soil samples every day to find the dryness or something like that, right? So forest fires is a very hard one. Things have been done with it, but maybe something like physics simulation, that we know is very accurate. So in short, yes, if something's wrong with the simulation, we're missing a detail, everything might be off. And it might be still a bit useful, but maybe not so much. So we do really need to make sure that the simulation is accurate if we want to transfer the knowledge learned in simulation to reality. That's a very important point, is making those accurate simulations.
Perfect. Shalev, unfortunately, time is up. I still have so many questions, so you need to stay with us for a bit longer. And as you can see, everybody in here is just like, okay, staring at you. We still have so many questions left. Please stay with us for a bit longer, but unfortunately on stage we have to come to the next session. Thanks a lot. Your round of applause. Shalev,
Thank you for the great
Lifshitz.
questions.